Good morning. Welcome to Krishna's class. The theme of this talk is how the Lebesgue measure can be constructed on RK. Recall that we have done it on R, but we did it from scratch, starting from Riemann integral, giving valid reasons for going for a new concept of integration, and thereby constructing uh, the concept of measure, which is a generalization of the concept of length to, if possible, for arbitrary subsets. Then we found that the so-called measurable class of sets which form a sigma algebra, so that is needed the moment we define a measure, is not the entire class of subsets of the real line, and in fact you have to throw away some sets which later we have shown that there exists non-measurable sets in the, and then for those sets which are measurable we have defined the measure, generalizing the concept of length for intervals. That means we approach through intervals. Okay, and for intervals the measure is taken as the length of the interval, and through that we defined the Lebesgue measure for the sets. In fact, you can do it for what you call outer measure for all subsets of R, out of which only a selected class of subsets have the countable additivity. Okay. So what we need is the measure on the countable union of measurable sets which are pairwise disjoint has its measure given as the sum of the measures of each of the components which make it. That condition is absolutely essential, and this essentially restricts the class of measurable subsets. So this is the sum and substance of that. Now if we want to follow the same procedure for RK, then we have to start with generalizing the concept of Riemann integration, which is there, to RK, and then almost mimic the entire procedure to arrive at what is called the Lebesgue measurable sets and Lebesgue measure. But what is special about the Lebesgue measure? Yeah. So now you see, before I make a statement about it, which we shall consider some detail, which is essential, we want to do the following. Okay, we want to choose an alternative route to the development on RK so that our work is very simple. And in fact, we have already got the tool. The tool is this, the Rees representation theorem. And what does it say? It says, suppose you have X, a locally compact Hausdorff space, that is the topological structure of the space X, and let lambda denote a linear function a positive linear function. Positive linear function on CCX. What does it mean? Lambda is a map from CCX. CCX is the set of all continuous functions, continuous real valued functions with compact support. This is what you call CCX. So lambda is a linear map from CCX to R if we are talking. Okay. Now, in fact, this is positive means that if f is greater than or equal to 0, then that implies it's positive. Okay. Now, if lambda is such a linear function, a positive linear function on CCX given by this, then there exists a sigma algebra on X there exists a sigma algebra on X which means a set of subsets which satisfy all the requirements of a sigma algebra, which means the empty set is in it, the whole set is in it, if A is in it, A complement is in it, and then it is closed under countable union, and from that you can also deduce that it is closed under countable intersection. Now this is the property of the sigma algebra. So the set that we obtain has the sigma algebra structure, and then so this say designated by script m and mu a set function. Mu a set function from M to R, mu of E is 0 and mu of actually R union plus infinity, or I will put it this way, I will write it here 0 to 3. That means it takes non-negative values and it may even take plus infinity. Okay. Then you have mu is countably additive. Now this actually restricts the number of it may not be the whole class of subsets of X which become the sigma algebra, but you may have to throw out some subset from Px because this particular condition cannot be satisfied. Okay. Now then x m is a measure space with mu signature is measure. Rather defining the measure. Measure. Okay. Further, lambda f equal to integral over x f. This is the integral. That's why we construct a concept of measure only to do integration. Therefore, you see that for all functions CCX, you have this relationship. And this is uniquely determined. Given lambda with all these features, there exists a unique measure, which means corresponding m and mu. Okay, so you have the relationship. So from lambda, so corresponding to each lambda with these properties, there is a corresponding. Okay, so this is a very general theorem that you have, right? But in this, at this stage, what we are trying to do is to get hold of the analog of Lebesgue measure on R in the case of RK. Is it possible? So that is the question. How Lebesgue measure on RK can be calculated? This is the question that we are asking. When we are going to use this route. Okay. So we shall explore how the Rees representation theorem can be made use of in the construction of Lebesgue measure on RK. That's our strategy. Here RK is a locally compact Hausdorff space. So there is a perfect ground on which we can explore this route. Because we start here, generally we start with a locally compact Hausdorff space. Now what we need is, we want the Lebesgue measure to emerge from our exercise, not any measure. Okay, this theorem is very general. If these properties are satisfied, that is, lambda is a positive linear function on CCX, then there exists a class of measurable sets associated with that, and a measure, so that xm mu is a measure space, and the linear functional and mu is connected through lambda f is equal to integral over x f. Okay, but still, therefore, you see that suppose what we intend to do is the following. Okay, we want to have x m mu with x equal to rk. So this is what we want. We want rk on which we want to define a class of measurable sets and mu the Lebesgue measure. So that's what we are after. So we want to get hold of, want to work on x equal to r. So what we are looking for is 8x equal to r. Now, how do we set up how do we choose a linear function? On CCRK, that means all k equal to 1, 3, etc. etc. Such that RK, we designate the measure, this RK M script M mu is measure space. Okay, so that we would have, if we are able to do that, so what do we have to do? We have to choose a positive linear function. So the question that immediately comes out is, x is such a see, we have some experience now. If x is r, that means k equal to 1, then we have such a linear function. If x is equal to r, that is r1. Okay, I'll put it here r1, which is equal to r. Then we know that such a linear function is on CCR exists and is given by lambda f equal to integral over x or r, x is r, f fx dx. Okay, because we see that this is a linear function. See, once the Lebesgue measure is defined, which becomes the Riemann integration. So in fact, this is actually integral R f dv, which is, I will put it in the right order. Integral dv. This is the Lebesgue measure, and this is essentially equal to integral over R fx. First of all, is this linear function defined? Now, f belongs to, it is compact circuit. So the function f is a continuous function with compact circuit. Therefore, this integral is essentially on support of f, which is compact. And this is a continuous function integrated over a compact interval, is essentially the Riemann integral. Okay, that Riemann integral, you know that once the Lebesgue measure is introduced and Lebesgue integration is introduced, for all Riemann integrable functions, the Lebesgue integral of f becomes the Riemann integral. Now this is the, therefore this equality holds. Okay, so that's what we have the connection. Therefore, we are working with lambda f equal to integral over R fx dx. Okay, and what is the analogous thing that we can do? So on RK, what do we do? Etc. Okay, we have to work with CCRK, and lambda has to be defined from CCRK to R, or R, and this should be something like this. Integral over RK here x consists of, see, dx stands for dx. Okay, it has to be this. Okay, so you have to have a knowledge of this, and what we are expecting is that since this is the generalization of this, we hope that the corresponding lambda will certainly, by Rees representation theorem, fix a measure space, and that measure space can be legitimately called the Lebesgue measure space. Okay, and then of course this becomes simply the Lebesgue integral. Okay, valid for more larger class of functions, in fact. Okay, so from this we can get to Lebesgue measure. But what is so special about that? See, the general theorem, when you apply, you get a measure. You get a measure space. You get a measure. But that is not necessarily the so-called Lebesgue measure. What is special about the Lebesgue measure? There are two things. Of course, apart from the general properties of the measure, so we will be working on what are called X. There will be a class of measurable sets. RK, measurable sets, and mu. Okay, this is what ultimately comes out to be, right? But on R, what are the properties that you have? See, the measurable sets, that means all open sets. Okay. All compact sets are going to be in M. So we have all compact sets in M with a finite measure. All open sets are in M. And we have what you call the okay. What we are looking for is this. The special properties, apart from what are the general properties that are stated in the Rees representation theorem, where you are assured that all open sets are going to be measurable, all compact sets are going to be measurable, and if E is any measurable function, then it can be either approximated from above. It should be something which can be approximated from within through compact sets, provided its measure is finite. Okay, so these are the special features that you automatically get from Rees representation theorem. But what more we are looking for? We would want the following characteristic properties. Of the Lebesgue measure valid. Namely, one measure of, or what you call the measure of E plus X. What does this mean? See, X is a vector, or E is contained in RK. X belongs to. So what is E plus X? E plus X is essentially the translate of E through the vector X. Okay, so in R2 it would be something like this. Suppose this is your E, and then you have a vector here. So you translate the whole thing through that vector. A similar It won't change in shape, but this is going to be E plus X. This is the vector X. So if you are taking a vector in this direction, then you are translating it in that direction. If you are taking a vector in that direction, so this is generally, see, you take a subset on the real line and translate it to the right or translate it to the left. Here you have all around translation possible through vectors. So this condition has to be satisfied. Now this is a desirable condition, or this is something, one of the features of the Lebesgue integral. The other property is that in R we have the measure of mu of an interval AB minus C, where AB is an interval. Whether it is closed interval or open interval, whatever it is. So I would, without causing any confusion, I will write it like this: mu of I, whether it is open, closed, or half open or half closed, this is equal to the length of or you can write this as, this is the second feature that you have. So what is the analogous property that you have in RK? Okay, right? So we have to work on that. So what are the analogs of the intervals? The analogs of intervals in RK are what is called K cubic cell, K cubes. What does it mean? It means the cells, see the k-dimensional cubes. What does it mean? Okay, let us take in 2 dimension. This is actually a rectangle. This is actually AB cross CD. This is a K cell. In 3 dimension, it is going to be a box like this, with the edges parallel to the coordinate axis. So what do you get? You want the area of this to be the measure, okay, and that is given by the product of the lengths of the 2 sides, 2 adjacent sides. Okay, in this case what happens? It is going to be the product of the lengths of the adjacent edges. That means this is going to be AB cross ED cross EF. So something like this. Okay. So more generally in RK it will be a k-dimensional rectangular parallel with edges parallel to the x-axis, to the coordinate axis. Okay, and what you get? You get this equal to the K cell or K hypercubes or K cell consists of hypercubes in RK with edges parallel to the coordinate axis. Then we want, suppose the K cell is equal to this set, product of Ij, where Ij is the interval something of the form Aj Bj or Aj Bj or where Aj, Bj are all elements of are real numbers. In fact, non-negative real numbers. Okay. Then volume of the K cell is what? The product of Vj minus H. Okay. Instead of the length of the interval, this. So what we want is this. So suppose E is a K cell, then we want the measure of the K cell equal to volume of that is given here. Okay, so that's what we want. We want the measure of the K cell should be equal to the volume of the cell. The first condition is that every measurable set, when translated through a vector, also should be a measurable set, and the measure of the original measurable set and the measure of the translate should be equal. The second condition is that for K cells, which are the analogues of intervals on R, generalized to Rk, then their measure should be equal to the volume of the K cell. Okay. In fact, this is not just this is the concurrence of the measure with our common notion of the measure of the case. Okay. So our the linear function that we choose on CC Rk has to produce a measure which satisfies these two conditions, in addition to what you automatically get from the application of the Rees representation theorem. That is the point. Okay. So the question is that now is how to choose such a linear function. So the problem now boils down to picking up the appropriate linear function. So reduces to an appropriate positive linear function on CCI. So that's our task. But how to get this? In R, we started with Riemann integration, and then we had the integral. We found that it is not adequate enough to serve our purpose. Therefore, we generalize this to get what is called the Lebesgue integration, and in the process, you got the Lebesgue measurable sets and the Lebesgue integral, which coincided with this linear function. So we go back to that and make an analysis how this particular thing can be done. For some more time, we stay with R. We go back to R. X equal to R. Stay with X equal to R. Okay. Now there, you recall the linear function turns out to be the Riemann integral of CCR. Okay. So we have to get the analog of that in RK, which we do not want to go through that laborious process of developing Riemann integral and then Lebesgue integral and so on there. But we want to use at one stroke this particular the powerful theorem, namely the Rees representation theorem. And there, the moment you define the positive linear function appropriately, everything comes out to be true. But let us see how this is possible. We work backwards. This is what we are doing. We work backwards from situation. So on X equal to R, now we take CC. So you take an F belonging to CCR. But what do you know? Which implies F is continuous on R. And as compact set. What does it mean? That means support of F equal to is a compact set. Which implies there exists a bounded closed interval, or I would rather use the terminology a closed bounded A, B, say such that support of F is contained in a closed bounded interval A, and outside in AB complement AB complement F is identically equal. So support of F on complement. Now suppose F is continuous and is essentially on the interval, on the closed bounded interval AB. Now you see that F is uniform. Implies F is uniformly continuous. F is uniformly continuous. So let us leave that there and we'll look at the consequence of this. Now this means, I'll put this here up. Then we have given epsilon positive, there exists delta positive such that mod fx minus fy is less than epsilon mod x minus y is less than delta. Now this is valid for every x, y belonging to not only AB, outside also, okay, belonging to R. Why? Because outside this interval, it is going to be 0. Okay, it's a continuous function, and outside this interval AB, the function is identically 0. Therefore, everywhere you see that this particular property is satisfied. From uniform continuity, this would follow. Now we are going to use this. How do we use this? So let epsilon positive be, and that is fixed now. Let delta positive be the corresponding charge as in the stated result. So epsilon is given, delta is chosen. Is once epsilon is given, that we fix, delta is automatically available, so that for mod x minus y less than delta, mod fx minus fy is going to be less than epsilon. This property is satisfied. Okay. See, this means the following. Suppose you have a function like this. Okay. Now you fix a epsilon neighborhood of that. Suppose this is your function. Okay. Now you fix an epsilon neighborhood. What is going to be epsilon neighborhood? It is going to be a road with width less than 2 inches. Now this is the road around the function, or what you call f plus epsilon and f minus epsilon. This is the function minus epsilon. Now what this theorem says is that if you take a delta neighborhood, say x, y, with delta for any choice of x and y, now you see that the deviation in f, that is, you take the maximum of f on this interval and the minimum of f on this interval, on the same interval, take the difference is going to be less than delta. Okay, so this is what you have, a supremum of x belonging to the delta interval minus infimum of f x belonging to I is the delta interval. They do exist. Okay, and this is going to be less than. Okay, so this is the result that you have from our construction. It follows from the uniform continuity of the function. Okay, now what we do? We do the following. Choose an interval, a positive interval, a positive integer such that one by 2 to the power n is less than delta. 1 by 2 to the power n is less than delta. Okay. Now what do we do? So let us go for a partition of R. Now write the whole of R. Write as the union of M into M by 2 to the power n to M plus 1 M belongs to, is an integer, belongs to Z. Okay, right? What do you get? Now, you know that on each of these intervals, I mean, they are all disjoint. That means if M1 and M2 are different, then that is whenever different from M. So this is a disjoint breakup of the whole of R. Okay. Now we shall define a new function. Define G from on what interval? AB or rather I will put it this way, on R by the following, by G equal to sigma. See, you have from what you have on this times take the minimum value. What is the minimum value, or what you call the minimum of F for F and the infimum exists, okay, times characteristic function of This is the definition of G. That means on the interval m by 2 to the power n to m plus 1 by 2 to the power n, you define the value of G to be equal to infimum of f on that interval. Elsewhere it is going to be 0. And h. Same sum m belonging to z supremum of characteristic function of so you have two functions now, G and H. G takes the value infimum of f on this interval taken over this interval on this interval. Okay. Similarly, it takes the supremum value of f on that interval. Okay. Elsewhere, these functions are going to be 0. And it is the sum of these functions. So what you are getting is a step function. Okay. Or what you call a simple function. Or here it is a step function because you are considering only intervals. Okay. Now, what is the difference between f and g? Just to look at it. Now, g is a step function. Not necessarily continuous. But support of G is again contained in that interval AB. Outside it is going to be 0. So H is likewise a step function with support AB and not necessarily continuous. We can define two functions. Now we shall use one of them. Okay, or we shall use both of them in our analysis. Now what we have is the following. Now G and H. So what do we have? G is a constant function on interval of the type m by 2 to the power n to m plus 1 by 2 to the power n. H is also a constant, takes a constant value on this interval. Okay. Now let us define the following. Okay. Right. So what we have is this. So if omega n is designated by a set of fold n, this is omega n. Then on each element of omega n, G and H are continuous, are constant or continuous. That is one of the properties. First property. The second property is that you have G is less than or equal to F less than or equal to H. G is less than or equal to F less than or equal to H, where F is a continuous function, whereas these two are not continuous. The third property is that G minus H or H minus G is H minus G is less than epsilon. Why H minus G is less than epsilon? The reason is that on each of these intervals, okay, that's an interval of a length which is less than delta. And therefore, on each interval of length less than delta, you see that if the value of fx minus gx is going to be less than epsilon. Therefore, here you can see that the way in which we have defined h and g, this difference is going to be less than epsilon. So these are the three properties that we have. Okay. Now you have. Now we define the following. We'll define two to the power minus n summation over of x belonging to the collection of points Pn x, okay, where Pn consists of all the points of the form what you call m by okay. So what you are doing is this lambda nf is defined as 2 to the power minus n times fx on this extreme. So the value of that function. So it's a constant. So let us do that. So let's just explain this out. So you have Suppose you have some f. Okay. Then what do you define as the value of f? The value of this lambda n f is defined as 2 to the power minus n. This is this one multiplied by the height f at m by. Okay. And then you have similarly the so this is your lambda n. Now let us see what happens. So you easily see the following. What is that? So you take lambda. What is that? Lambda n. We have already chosen n g. Because the extreme end value of g is going to be the infimum of f. Okay. Therefore, this is going to be equal to, by definition, 2 to the power minus n summation over x belonging to Pn. What is this? Okay. G. What is the value of G? G is actually equal to 2 to the power minus n sigma infimum of x belonging to m by 2 to the power n m plus 1 by 2 to the power of fx, because it's just a constant value. Okay, that is lambda n g. What about lambda n h? This is the one. So m equal to so you have these two functions. Now note that finite sum. So also is a finite set. So we need not be alarmed by seeing the infinite summations, right? Most of the terms are going 0. All but finitely many terms are going 0. Therefore, this is finite. Now it is easy to see what happens. Now you can see that lambda n g is equal to lambda n g for n, any n greater than or equal to. Why it is so? See, we are taking this one. This is what you call m by 2 to the power n. This is m plus 1 by 2 to the power n. Now, suppose you take any n greater than n. What happens? It is going to be the further subdivisions of this interval. And everywhere here the value of g is the same. Therefore, this sum does not change at all. Okay. Similarly, lambda n h is equal to lambda n for every n greater than n. Because this is the reason. We are taking this interval, subdividing it. Okay. Therefore, the relevant sums are going to be those values of these points which are where the function takes the same value. Therefore, these sums are going to be essentially the same. Okay, right. Therefore, we have the following inequality. Which is less than or equal to, what is it? From the definition, this is going to be lambda n which is less than or equal to lambda n. Oh, I'm sorry, I think I should be writing h. Lambda n h which is equal to so what is the consequence? The consequence of this is that, you see, this is going to be on each interval this is going to be less than epsilon. Therefore, what is the consequence? The consequence is that the upper and lower limits of which gives this one and this one, okay, differ only by epsilon time epsilon times sum of, I mean, you know, these intervals, you take the union of all these intervals, what do you get? This is, you see, the relevant one is now, you see, this partition is relevant only on the interval AB. So, times B minus A, where B minus A is the length of AB containing support of okay. So it is going to be at most they differ by these two differ. So what one gets is this. This is the result that we. What is the meaning? One is an approximation from above, the other one is an approximation from below. Okay, so you are approximating f from above and from f from below. Therefore, what happens? This implies limit n tending to infinity the limit exists, and call this the lambda f. And this turns out to be, this lambda f, see if you carefully examine, you see that this is going to be what is called the approximation that is involved in the Riemann integral. This turns out to be essentially equal to integral over r f x dx. Okay. So as I said, from here you go over that. Therefore, what you have? So from here you go over. Therefore, the problem is to get this lambda f. This lambda f can be defined as the limit of n tends to infinity of lambda n f as constant. So this lambda f can be recovered as the limit of lambda n f. Infinity, which is nothing but what we do in Riemann integration. What you call the upper integral and the lower integral. So lambda n is the lambda n g is the lower integral approximation of the integral. And lambda n h is the upper Okay. So how do we proceed now? So in RK, we can find as the, see, instead of here 1 by 2 to the power k is the length of the interval, but we work on the cube, k cube. Therefore, the volume of that is going to be 1 by 2 to the power k kn now here Pn is going to be not a single point, but they are going to be with coordinates, n coordinates. So you have and then take this as the limit of, take lambda if and take which exists. In the case 1, so in the case k equal to 1, this is the Riemann integral. R means, I mean, essentially on just be careful because Riemann integral is not defined on the infinity interval. That's why I'm saying it is essentially on A. You can drop this and say this. So that's our strategy. Okay. So I think I stop here. Thank you very much. Now we will just conclude here and then we continue with it in the general case next time.